some research that I've been doing over the last year or so. And really, it's motivated in part by both the sobering and exciting implications of developing lunar space beyond the geosynchronous regions of geo for the purposes of both exploration and development of the moon. And but this area has really breathed new life into the field of astrodynamics, similar to what the exoplanetary science and the celestial mechanics. But it actually requires, in this case, a more fundamental understanding of the multi-scale dynamics within this regime, which has been largely uncharacterized beyond mission timescales. So the nonlinear astrodynamics in, let me go back real quick. This is in the background slide. This is the orbit of the Transit Exoplanetary Satellite Survey. So it did a phasing orbit to become in line with the lunar flyby, and it used that flyby to establish its current operation area, which is a 2-to-1 lunar mean motion resonance. This is the second time that a spacecraft has entered into a mean motion resonance with the moon, and we'll talk about the stability of these type of orbits here. All right, so the nonlinear astrodynamics in the cislunar region, this is in XGO is what we're primarily concerned about, encompassing resonant, secular, chaotic, post-encounter dynamics is drastically different than the weakly perturbed Keplerian approach that is used for over the past half century for the detection and tracking of objects near our Earth. And so the main objectives of this research are really to apply a Hamiltonian formulation to determine the strength and the width of the stable vibration zones of the predominant mean motion resonance of the 2-to-1, 3-to-1. These are currently used by IBEX and TESS. And really, to answer the more general question of what is the Kirkwood gas of cislunar space, and this is a question of great relevance now that we're locating our space-based assets in these regions, which we only loosely characterize their stability. We'll also adopt some tools and techniques from solar system dynamics to apply really dynamical cartographies of the phase space in order to leverage this for space surveillance and catalog maintenance. So if we understand the transit and visit rates of these objects in the phase space of the orbital elements, we can use this for space situational awareness and domain awareness for purposes of tracking and maintaining the catalog. And then lastly, just like our near-Earth terrestrial, circumterrestrial domain, it's important to have a little bit more forethought in the design and operation planning of missions because we want to avoid the unfettered debris growth that has plagued the traditional zones. And of course, the dynamics are very, very chaotic and complicated. So it's more important to have a characterization of these as we go forward. So this, I want to say that despite all of the different types of dynamical features that exist in this regime, it's really only the vibration point orbits and their associated myriad manifolds, things that were talked about in the last two presentations by Ross and Guzzo, that have really been coupled to the cardinal questions and problems posed by space domain awareness. And really, we don't have an accurate characterization of the long-term stability of chaotic, secular, and mean motion resonances that pervade this regime as well. And the connection between how do you transfer strong mean motion resonances, which are going to be used for constellations of satellites in the near future as parking orbits for lunar exploration and the like. How do we connect the dynamics of these vibration point orbits and the different time scales, multi-time scale dynamics that is involved? And of course, this is very important because of the future development. So that's a very large regime to cover. Shown in this figure here is the highly perturbed dynamics of a very elongated, distant satellite, the Soviet third space probe, Luna 3, that circumnavigated the moon and suffered. I thought you were on this topic. And suffered 3 close approaches of the moon. This is the first actual gravity assist, and it was designed to return after its first passage into an orbit so that it can relay the first pictures of the far side of the moon to the Soviet stations. They actually lost track of the satellite after this. This predated the Voyager gravity assist. So this was the first gravity assist ever designed in astrodynamics. The interesting thing, though, about this spacecraft is that despite being its periaxis or perigee being larger than the distance of geo, 7 Earth radii, after 11 revolutions it plummeted to the Earth. So it didn't crash into the moon, it actually re-entered the Earth because of the effects which are going to be driven up by what is now known as Leadoff Kozai or Leadoff Kozai von Mosaical, how many names we're going to associate with these effects, but with a nonlinear secondary resonance that competes also with the close encounter dynamics. And so this is just, at a more fundamental level, now that these same flybies have been used to establish both the IBEX and the test operational orbits. These guys are similarly affected by such long-term and I would say medium-term and even short-term type dynamics. So it doesn't exactly follow these contour curves of the Hamiltonian associated with the Kozai cycles, but it loosely does because we know that the quadripolar approximation for the solar perturbation is well governed by this phenomenon. Now the moon, given the distance of it, it breaks a number of those assumptions made. So you have to take the order of the Legendre polynomial to much higher degrees to get an accurate representation. But to some level, this allows us to study what is happening, what is driving up the eccentricity of these distant space probes. Despite this being one of the most important phenomenon in solar system dynamics, and dynamical astronomy in general, mean motion resonances have largely been unstudied in the circumterrestrial regime, in part because most of our satellites that we launched today have been too low to be affected by any mean motion commensurability, even with the moon. The situation is different now that we are locating some of our important space-based assets, IBEX, tests, in these predominant mean motion resonances, which have only been characterized to a very loose degree. I want to say that, so one of the questions that I've asked is what are the Kirkwood gaps of cislunar space and why are we locating our spacecraft in those gaps? IBEX actually is a very interesting spacecraft because it was launched in an orbit very close to the 3-to-1 mean motion resonance of the moon. And then they were given an extension on the mission, so they did a covariance analysis on the predicted position. You can see that in this scale, you can't really see much difference in the Monte Carlo simulations that they did. But after about 2.5 years, the spacecraft could be anywhere from crashing into the moon to crashing into the Earth to ejecting into Earth into space. So this prompted them to, with the limited fuel they had, they designed a novel 3-to-1 mean motion resonance, and they established that operational orbit by doing a lunar flyby. And you can see in the rotating the synodic frame that the moon always is up here in this figure, so it sort of avoids the perturbations caused by the moon. So you can feel it in the base space. It's actually in the stabilization zone of the 3-to-1 lunar mean motion resonance. Now, I don't think that's a particularly useful operational design, even for its extended mission, because now IBEX is going to be a long-lasting debris even after its sustained mission is over. So it's going to be in a stable regime for hundreds of years now. So what they could have designed, using more insight into the base space topology of these resonances, they could have put it in a vibration zone, but closer to the separator, so that at the end of the life, they can just do a short nudge and get that spacecraft out. And this is for really space sustainability purposes. Now, TESS followed suit, and it's orbiting in a 2-to-1 lunar mean motion resonance. Here, the moon is on the left, and this guy here is also very long-term stable, as you can see. One of the things in astrodynamics is that most folks in the space surveillance and space nutrition awareness communities believe that these orbits cannot be parameterized with classical orbital elements. Of course, that is not the case. It's only true for vibration point orbits, but in that case, we can switch to a piecewise description of the orbital element distribution in either synccentric or geocentric elements. But what I showed here is a really just about a 2.5-year evolution of the TESS spacecraft. And those circles here are the ephemerides from NASA Horizon system. The triangles here are the 2-line elements that's reduced space. So even the catalog can maintain the project pretty well. But what it takes to actually reproduce this trajectory is a ephemeris model of the restricted 4-body problem, the Earth, Moon, and Sun system. So even at the basic fundamental level, the circular restricted, or even the restricted theoretic problem, even the elliptical one, does not reproduce the ephemeris of these motion resonant spacecraft on these even shorter, what we would consider shorter times as well. This is about 1,800 orbital revolutions of the spacecraft. All right, so if we go to something that was launched in the 1960s, is the eccentric geophysical observatory spacecraft, and they early on they predicted that it would re-enter in about 18 years or so. In fact, it only decayed in August of 2020, in part because it was on the cusp of orbital stability and instability due to secular resonances. This shows here a multi-decadal evolution of the Vigo satellite from the epoch of about 2002 when we acquired it in the space catalog. This is the initial sort of sparse data that was shown, and there's about a 30-year gap in the catalog for the spacecraft. Tracking is not a very, very difficult problem. So one of the interesting things to note, though, is that had they just delayed the launch by 10 minutes, or advanced the launch by 10 minutes because of the orientation of the Earth, Moon, Sun system and the secular resonances that are affecting the dynamics, this spacecraft would have actually re-entered a long time ago instead of being this long-lasting LEO to GEO crossing debris. So, and when we think about the dynamics of these type of objects, fitting solar system counterpart is, of course, the centaurs. It's the highly dispersed population of small bodies between the orbits of Jupiter and Neptune, and that are affected by, of course, many different dynamical phenomena, from primarily mean motion resonances to even in this inlet here, some work by recent work by Guzzo and some work by Howell and Ross earlier on shows that these objects actually can transition on account of manifold dynamics to becoming different dynamic classes to these Jupiter family comets and the like. So we want to analyze, and of course, this is all the allowable eccentricities and differences in the axis. So we want to study the problems of the dynamics of these distant Earth satellites that are affected by the gravitational force of the moon and the sun. We have to start adopting some of the tools and techniques that have been used to characterize highly eccentric and highly distant orbits in the solar system. This is some more recent work by Renu Malhotra that studied the structure of the of Neptune's mean motion resonances from doing basically at high eccentricities, and this is done by doing whole-grade surface section at each of those various parameter spaces and characterizing the size of the vibrations. And it's very computationally tasked work to characterize what these. There's also been work by this morning and Sylvia Paz-Malo, earlier work by that on characterizing the structure of resonances for high inclination and high eccentricity, which is something that we often didn't see in classical traditional asteroid belt and regime. So this is some work that I've been using to adopt to the astrodynamics context of cislunar space. And another work is by Gallardo. There's a number of series of papers and also some tools that he provides on characterizing the resonance strength and the width of the predominant mean motion resonances from the lunar solar system all the way out to scattered disk. So this just shows the traditional domain. And one of the things, he has a technique that is just based on Hamiltonian Formulation theory, but it's a numerical technique to compute the to formulate the reduced Hamiltonian for the resonant motion, and then to do a level curve similar to what we see for the Kurzweil leadoff cycles in order to produce the similar type of surface effect base portraits that Malhotra had done for the Kuiper belt. And so there's a number of different techniques from fully numerical to getting a reduced order model to characterize these resonances. A number of the things that concern us, though, is that the expansion for the third body perturbation for the moon is quite involved, and these Taylor series expansions often involve genre polynomials, which have a convergence, a very slow convergence do the full discerning function for the third body perturbations. And so you have to keep a lot of terms in the secondary Hamiltonian order, in the resonant Hamiltonian order to find out which one of those critical arguments gives rise to the dominant resonances for these regimes. So it's a significant amount of analytical work involved in this. And this is only some preliminary work that I've been doing on adapting Gallard's technique to characterizing these guys. One of the things I do want to point out, though, is that the moon Earth satellite dynamics is quite different than in the even in the solar system dynamics context of small bodies, in part because the most fundamental model, the restricted three-body problem, does not apply for the purpose of doing long-term dynamical evolution, and even in the short term. So this is that same test orbit. This is over a 30-day, so just 2-day orbital period. It's quite highly perturbed. This top curve is done with the restricted four-body problem in the ephemeris model, and this purple curve here is the restricted three-body problem. So we take the moon, of course, to have its eccentricity. So in the basic the basic dynamical model that would characterize the resonances, which we all use to come up with even when we look at the libration point orbits and their variant manifolds, that breaks down to these particular orbits. So we really have to adopt a more complicated dynamical model, so it complicates a number of the work in the Hamiltonian system. And also, the moon's orbit is highly perturbed by the sun, and so we have consecutive resonances embedded in those resonances, so it becomes a very, very complicated problem. And perhaps there's some work to talk about. There's probably some work in exoplanetary science that has looked at these type of similar dynamical problems. So another approach that has been used is to just do dynamical cartography. So what is shown in this map, of course, we can do these using any first order stability indicator like the FLI or the mean exponential growth or the nearby orbits NEGNO. NEGNO is built into rebound, so that's what's done in this example. And then computation of these stability indicators and the grid of orbital elements will allow us to really uncover some of the phase-space structure of these. We can see already. So already this is the orbit of IBEX. Nominal operational orbit was yes, this has been for portion is here at about 26 Earth radii. The moon is at about 60 Earth radii. And so if we compute these FLI here, we can see that IBEX is actually on the cusp of these unstable regimes, whereas just a short, small change in its major axis could have put it in the libration zone of that 3-to-1 resonance, which is where it's currently located now. So this a priori dynamical analysis could be built into mission design in this regime to allow us to really have a sustainable long-term exploration program for system or space. Some of this was kind of done for the orbit of test. Of course, we designed the orbit of test based on IBEX, but even in this case, you can see that the region is in general. This is a time scale of only several years, and we have gross instabilities as we get closer to the orbit of the moon. And sort of as we talked about, as Christos talked about the wisdom criteria, we're going to have I forget what it's called, the planetary clearing zone. So that's very prevalent for the Earth and the Sun system, and having the timescales equivalent to what we consider mission timescales. So we can also do these type of dynamical maps over much shorter timescales to reveal the structure and orbital element space of the structure in the orbital space of the libration point orbits and their variant manifolds. And this is something that connects really the geocentric and selenocentric orbits. So these, of course, governed by the perturbed two-body problem to the libration point orbits, which are governed by the restricted three-body problem in a holistic fashion. So shown on the top panel here is done with the restricted three-body problem. So just taking the moon as a perturber, and we get a little bit different features that manifest on these short time scales when we add in the sun that cannot be ignored for the purposes of really tracking and catalog maintenance of cislunar objects. So this is some interesting dynamical maps that we're still really trying to understand at a more fundamental level. So I wanted to end there. I think I'm almost out of time here, but so a lot of this work was motivated in part by some of the earlier work by myself, Jerome Decon, and Alejandro Rossi and others on understanding how to use resonances in Galileo, GPS, and medium Earth orbit regimes to render space more sustainable. Find the ocean gyres of space, the regions where you can park orbits, park satellites so that they will be long-term stable, and also where you can put them in regimes that will allow them to with a small maneuver to re-enter the Earth. So this is the dynamical theory of resonant orbits. This is a quote I like by Slawomir Brider, who done some early work in the 2000s on characterizing all the semisecular and secular resonances that affect Earth satellite dynamics. And the problem with that research, at least because I'm a professor in an American institution, so I don't really get to do research anymore. I get to apply for funding, justify my my application. The timescales for those resonances that affect the sort of traditional LEO to GEO regimes are several hundred years. So you tell someone that we're going to put something there, and 20 years, I promise it'll be gone, or 50 years it'll re-enter. It's not as lucrative and as compelling for them. But when we get into this lunar regime, it's really where the XGO regime is really where these dynamics take place on mission timescales. So it really motivates a lot of the understanding that I want to do for this area. So I'll end with this quote by Slawomir Brider that in contrast to the widespread cliche, the satellite problem. So this is the early work by Brower, Kozai, and Garfinkel in the late 50s Sputnik era. Really requires now fundamental research on a level that is more than just tracing the microscopic influences of these Tesla harmonics, which has been really what people think of astrodynamics before. So we really have to do a lot of the phase-based topology and uncover the resonances and link them to transfers within this regime, similar to a gamma and other things. How do we go from mu motion resonance to mu motion resonance? The vibration point orbits, we use these as parking orbits as well. And how do we link that to space sustainability? And that's one of the topics that I'm investigating going forward. Yeah.